So, how do you count something you literally can't see? Today, let's talk about the mole. Yeah, this was a huge problem for chemists. How do you actually work with atoms?
They're just way too tiny to count one by one, so they needed a clever trick.
The big idea? Create a kind of universal weighing scale. Just compare atoms to a standard. This gave us relative atomic mass, or RAM, and carbon-12 became the universal benchmark. But knowing how heavy they are isn't enough. For reactions, you need an actual count. I mean, think about it. We use special numbers like a dozen all the time. It's just 12. Right, but for atoms, a dozen is nothing. They needed their own kind of super dozen. And that's where the mole comes in. It's basically just the chemist's version of a dozen.
And just how big is this number? Well, it's this, a mind-bendingly huge number.
We write it like this to keep it simple. It's called Avogadro's constant, 6.02 times 10 to the 23rd year. Okay, so here's the real magic. The mole is a bridge from the atomic world to ours. It lets us easily jump between the number of particles, their mass, and even gas volume. Molar mass is how we get to mass, and get this, its value is the same as the RAM.
And for volume, that's molar volume. But heads up, this one's just for gases.
You'll notice the volume changes with temperature and pressure. That's why we have standard conditions. Okay, so we can measure stuff. Now let's see how it helps us decode chemical recipes. A balanced equation is just a recipe. Those big numbers tell you the ratio in moles. This whole process of using mole ratios for chemical math, it's called stoichiometry.
And look, it's usually just a simple 3-step process. Go to moles, use the ratio, convert back.
All right, key takeaways. RAM compares mass. The mole is that huge number for counting atoms. The mole lets us count them, measure them, and predict exactly what's going to happen in a reaction. It literally connected two worlds. So what else could a number like this help us figure out?